cross product is denoted by A cross B. So if we have got any two vectors A and B, and if we want to find out the cross product between these two vectors, then this resultant is known as A cross B. Now A cross B is equal to the magnitude of vector A into magnitude of vector B into sine theta into n cap. Now what is this n cap? N cap is a unit vector perpendicular to the plane of A and B. Now let us consider this plane. Vector A lies in this plane, vector B lies in this plane, and theta is the angle between these two vectors A and B. Now the cross product A cross B is equal to the magnitude of this vector A into the magnitude of this vector B into sine of theta into n cap. Now n cap is a unit vector which is perpendicular to this plane. So this black vector denotes A cross B, and this is along the unit vector n. N is a unit vector which is perpendicular to the plane of A and B. Thus A cross B is equal to modulus of vector A into modulus of vector B into sine theta into n cap. The theta is the angle between these two vectors, and n cap is a unit vector perpendicular to the plane of A and B. Now in which direction would n lie? This is determined through the right hand thumb rule. What we do is we curl our fingers from A to B, and the direction of our thumb denotes the direction of A cross B. As we can see that this is the figure which denotes A cross B. We curl our fingers from A to B, and the direction of the thumb gives us the direction of A cross B. Now let us try to understand some of the properties of cross product. The first is A cross B is equal to minus of B cross A. So we can say that it is non-commutative. Thus the cross product, unlike the dot product, is non-commutative. The second is vector A cross vector A is equal to 0. Now this is because the angle between these two vectors A and A is equal to 0, and hence sine of 0 degree is equal to 0, and so vector A cross A is equal to 0. We can also say that the cross product of any two parallel vectors is equal to 0. The third property is I cross I is equal to J cross J is equal to K cross K, and this is equal to 0. Now this is because again the angle between these two vectors is equal to 0 degree, and hence sine of 0 degree is equal to 0, and so this is equal to 0. The fourth property is A cross B plus C is equal to A cross B plus A cross C. This is known as the distributive law of cross product. So A cross B plus C equal to A cross B plus A cross C. The fifth is if A cross B is equal to 0, then A and B are collinear vectors. So if A cross B is equal to 0, we say that A and B are collinear vectors, or they are parallel to each other. The sixth property is I cap cross J cap is equal to K cap. J cap cross K cap is equal to I cap. K cap cross I cap is equal to J cap. J cap cross I cap is equal to minus of K cap. K cap cross J cap is equal to minus of I cap, and I cap cross K cap is equal to minus of J cap. So this is very important. The seventh property is if vector A is equal to A1 I cap plus A2 J cap plus A3 K cap, vector B is equal to B1 I cap plus B2 J cap plus B3 K cap, then A cross B is equal to the determinant, the elements of which are I cap, J cap, K cap, A1, A2, A3 and B1, B2, B3. So A cross B is equal to this determinant. Now when we expand this determinant, we get A cross B equal to A2 B3 minus B2 A3 times I cap minus A1 B3 minus A3 B1 times J cap plus A1 B2 minus A2 B1 times K cap. Thus A cross B is equal to this determinant. So if we have got any two vectors in three-dimensional space, then the cross product of these two vectors is equal to this determinant. The eighth property is if A and B are the adjacent sides of a triangle, then the area of this triangle is equal to 1 by 2 into modulus of A cross B. So let us consider this triangle. We see that AC and AB are the two adjacent sides of this triangle, and AC is given by vector A and AB is given by vector B. then the area of this triangle is equal to 1 by 2 into modulus of A cross B. The ninth property is, if A and B are the adjacent sides of a parallelogram, then the area of this parallelogram is given by modulus of A cross B. Let us consider this parallelogram OACB, where OA and OB are the adjacent sides given by the vectors A and vector B. Then the area of this parallelogram is given by modulus of A cross B. Similarly, if we say that A and B are the diagonals of a parallelogram, then the area is given by 1 by 2 into modulus of A cross B. So if we say that this is a vector A and this is vector B, where A and B represents the two diagonals of a parallelogram, then the area of OABC is given by 1 by 2 into modulus of A cross B. So having seen the cross product, let's try to solve an iitjee problem. This problem appeared in iitjee 1998, and it says that for any two vectors v and u, prove that the first is u dot v whole square plus modulus of u cross v whole square equal to the square of magnitude of u into the square of magnitude of v. And for part B, we have to prove that 1 plus the square of modulus of u into 1 plus the square of modulus of v is equal to 1 minus u dot v whole square plus modulus of u plus v plus u cross v whole square. So in this problem we have been given two vectors and we have to prove these two results. So let's try to solve the first part. Let theta be the angle between u and v. So let us say that theta is the angle between any two vectors u and v. Then u dot v would be equal to modulus of u into modulus of v into cos theta, and similarly u cross v would be equal to modulus of u into modulus of v into sin theta into n cap. Here n cap is a unit vector perpendicular to the plane of u and v. So from this we get u dot v whole square would be equal to u square into v square into cos square theta, and similarly u cross v whole square would be equal to u square v square into sin square theta. So when we add these two terms, we get u dot v whole square plus u cross v whole square equal to u square v square, and which is equal to modulus of u whole square into modulus of v whole square. Thus we have proved the first part, and similarly you can prove the second part. This is left as an exercise for you to prove. Now the next type of product is scalar triple product or the box product. Now till now we have seen the product of two vectors. Now let's try to see the product of three vectors. Now scalar triple product is represented as A cross B dot C. Now we know that A cross B represents a vector, so again we can multiply it with another vector, and this time this product is the dot product. So first we take the cross product and then we take the dot product. So this is represented by A cross B dot C. Also it can be written as this way, ABC. Here we see that it is enclosed in the bracket, and so this is called as the box product. Now if we consider this parallelepiped, then let us say that this is the point O, this is A, this is B, this is C, and so OA is represented by the vector A, OB is represented by the vector B, and OC is represented by the vector C. Then the volume of this parallelepiped is given by this box product. That is why it is also called as a box product. This is because it represents the volume of the box with A, B and C as the coterminous edges of this box. Thus the box product represents the volume of a parallelepiped with A, B, C as the coterminous edges. So the geometrical interpretation of scalar triple product is that it represents the volume of a box with A, B, C as the coterminous edges. Now let's see some of the properties of this box product. The first is A cross B dot C is equal to A dot B cross C. Thus we see that on interchanging the dot and the cross, the value of box product remains the same. So we can interchange the position of cross and dot. That is, we can put a dot over here and put a cross over here, or we can put a cross over here and dot over here. Thus the value of the box product remains the same even on interchanging the dot and the cross. The second is, if vector A is represented as A1i cap plus A2j cap plus A3k cap, vector B is represented as B1i cap plus B2j cap plus B3k cap, and vector C is represented by C1i cap plus C2j cap plus C3k cap, then the box product of ABC is equal to the determinant, elements of which are A1 A2 A3, B1 B2 B3 and C1 C2 C3. So the value of box product is given by this determinant, and the important point to note is box product always gives the scalar quantity. That's why it is also known as scalar triple product. Now the third property is the box product of ABC is equal to the box product of BCA is equal to the box product of CAB. Thus all these three box products are equal. Now consider this circle. This is A, this is B, this is C. Now BC, this represents a cycle. So if we take A, B, C here, B, C, A or C, A, B, that is, if the cycle is maintained or the cyclic rule is maintained, then the value of all these three box products remain the same. But if we change the cycle, that is, if instead of BCA we have got BAC, then this value would be negative of ABC. Thus for box product the cyclic rule applies. That is, box product of ABC is equal to the box product of BCA, and which is equal to the box product of CAB. The fourth property is the box product of A plus B C D is equal to the box product of ACD plus the box product of BCD. So we can split this as two box products which are equal to ACD plus BCD. That is, we split this term as A and B, and thus we get the box product as ACD and BCD. The fifth property is the box product of K times A B C is equal to K times box product of A B C. So if we have A as a multiple of K, then we can take K out of the box and get the value as equal to K times the box product of A B C. The sixth and a very important property is if three vectors A, B, C are coplanar and non-collinear, then the box product is equal to 0. Thus, if three vectors are coplanar and non-collinear, then their box product is equal to 0. And this is a very important condition for three vectors to be coplanar. So, if we want to prove that three vectors are coplanar, then prove that their box product is equal to 0. So now let's try to solve an IT problem. This problem